Alright, exercise 6.6. The points A, B, and C with those coordinates lie on the plane pi2. Find the equation of the plane pi2 in the form r dot n is equal to d. So n is a normal vector and r is an arbitrary vector that goes from the origin to a point in the plane. So in other words, that's your x, y, z vector. Okay, let's draw a little sketch. So this can be our plane pi2. Okay, and then we have the points A, B, and C in the plane. So A, B, C. And then let's let, so origin can be over here. Let's let A be our initial point in the plane. And so let's go ahead and calculate the vectors AB and AC. So the vector AB is equal to OB minus OA, so 10 minus 4 is 6, 5 minus 2 is 3, and 2 minus 3 is negative 1. The vector AC is OC minus OA, so 4 minus 4 is 0, negative 1 minus 2 is negative 3, and 5 minus 3 is 2. So now we can calculate our normal vector n. In this diagram it's going to be AC crossed with AB, but it doesn't really matter. If you do AB cross AC, you'll get an equally good normal vector in the other direction. So just cross one of them with the other. It really doesn't matter. So n is equal to, let's say, 6, 3, negative 1, crossed with 0, negative 3, 2. And that's going to be 3 times 2 is 6, minus 3 is 3, and then it's going to be 0 minus 12, so it'll be negative 12, and then finally it's going to be negative 18 minus 0, so that's negative 18. And we can take any multiple of that we like, so let's divide everything by 3, so 1/3 n is equal to 1, negative 4, negative 6. Okay, and so then we can get our equation of pi2 in this form here. So we have r, which is x, y, z dot n. So this is our new n, 1/3 of n actually. So it's x, y, z dotted with 1, negative 4, negative 6. We know that's equal to any random point in the plane dotted with 1, negative 4, negative 6. So let's just take A. That'll do. So 4, 2, 3 dotted with 1, negative 4, negative 6. Okay, and then we can leave it like this because this is r dot n, which is what the question asked for, but I mean you can expand it out easily as well if you want. But anyway, the d value is this one here. It's a scalar because it's a dot product. So it's 4 times 1 is 1, so minus 8 is negative 4, and then it's minus 18, so that'll be negative 22. And let's just expand it out anyway. So x minus 4y minus 6z is equal to negative 22. So that's our pi2 equation. Right, and next up, we're told that the point D, which is 1, 3, 5, lies on the plane pi3, which is parallel to pi2. So pi3 is parallel to pi2. That means that any vector that is normal to pi2 is also going to be normal to pi3. So we already know that the equation of pi3 is going to look like this. But we can use the same n vector, so it's going to be x minus 4y minus 6z is equal to some d value. And to find the d value, we can just observe that this point, x equals 1, y equals 3, z equals 5, is on the plane pi3. So point D, which has coordinates 1, 3, 5, is in pi 3. 1, 3, 5, yep, is in pi 3. And since this Cartesian equation here, x minus 4y minus 6z equals d, this is the equation that determines all of the x, y, and z points, x, y, z points in R3 that compose the plane. This any x, y, z point in R3 that makes this equation true is in the plane pi 3, and any x, y, z that does not make the equation true is not in the plane pi 3. Well, since D 1, 3, 5 is in pi 3, that means x equals 1, y equals 3, z equals 5 makes the equation true, and so that allows us to find D. So 1 minus 4 times 3 minus 6 times 5 is equal to D. So D is equal to negative 11 minus 30, so that would be negative 41. And we need the equation of pi 3 in the form r dot n equals D. No problem. So we have r is x, y, z, dotted with our normal vector, which is 1, negative 4, negative 6. This is equal to our d value, which is negative 41.